Hear me okay? I'm in the trough of my jet lag, 3 days. So 14-hour time difference, so I hope I don't sound too moronic. That's how I feel. Okay. Maybe 30 seconds on why China. Well, some of the cities in the eastern, particularly the southeastern part of China, are growing 15, 20, and the richest city in China, Xianjin, is growing at 30% a year. So there's tremendous growth and hence tremendous opportunities. So I can now use myself as an example of what's possible. I mean, I just walked in and I said, I want an E guy, I want a robot guy, I want postdocs or professors, and they just gave it all to me. 200 square meter lab. When word gets out, well, maybe another 10 years. Okay. So what am I trying to do? Basically, I evolve. So I use genetic algorithms to evolve neural network modules. And you can buy fairly cheap accelerator boards about this size. They're $1,000 or so, a bit more. And with those, you can accelerate the evolution of these neural nets about 50 times faster than you can on a PC. So then you evolve large numbers, tens of thousands, probably up to about 50,000 of these neural net modules. You download them into the PC. So the whole approach is very cheap. It's just literally a few $1,000s. That's all. Because it's PC based, the artificial brain itself is situated in the PC, and then you use that artificial brain usually via radio control, two-way radio antenna, to control robots, for example. So Chinese have given me 3 million RMB, of course, but then you have to consider the purchasing power. So it's equivalent to like a nice fat $3 million grant in purchasing power terms, which is nice. But pressure's on because I'm being paid about 6 times what Chinese professors would get. So I really have to deliver in the next 2 years. But I'm told if I do a good job, there will be more millions. So that's nice. Okay. Somewhere between 10,000 and 50,000 individually evolved neural networks together, connect them up in interesting ways, and that's the challenge. Of course, that's the research challenge. What can you do with an artificial brain that, by definition, is a network of networks, a network of evolved neural networks? Okay. So the accelerator board contains a chip, about 3 million logic gates, I think. The latest version, a bit more expensive, double that. So Moore's law is definitely working. The whole approach is very cheap, so I hope it'll be popular. Other groups will use it. Here's the actual board itself. It's about this big. The company involved making this is Soloxica. They're a British company. And you do not have to be an EE. You don't have to know like VHDL or those kinds of electronic design languages. It's much easier than that. You just simply write C, almost C. It's a version of C called handle C. It's about 80% the same as C, and that gets hardware compiled into this FPGA here. So anyone can do it. It's sort of simple. You just write your code. It gets compiled directly into this chip and runs at electronic speeds. So it's the 50-fold speed up. Other applications, people are getting like 200, 300 times speed up. Now, just quickly, I've been trying to do this kind of thing for a long time. I was 8 years in Japan in the 90s, and the Japanese built this very expensive machines, like $500,000. So if I go back, I mean, here's what, $1,500, and this is $500,000 doing the same job. That's Moore's law for you, right? So that's a really good case in point. Okay, so back of the envelope type calculations, how many people would you need to make a minimum artificial brain of, say, 10,000 modules? And with very conservative assumptions, so 4-year period, 50 working weeks per year, 5 days a week. Here's the conservative estimate. If one, I call them BAs, brain architects, if they conceive and evolve only 2 neural net modules per day, how many people would you need over that 4-year frame to produce a brain of 10,000? Well, you do the math, it's pretty simple. It's about 5. Well, that's the number I have at the moment. Although I could get as many master students as I want, and probably 2 or 3 PhDs. Okay. Now, I hesitate. Should I emphasize that this is a method, or should I put more emphasis on the architectures? I'm sort of torn. It's sort of both. I mean, the method, I think, is important. It's cheap, it's fast, and it works. Right? So hopefully other groups will do it. And then common sense says each group will have its own architecture. So there'll be many different architectures. So should I focus on my group's particular architecture?
Focus on your architecture.
Okay. All right. So the big challenge now is what can we do with several tens of thousands of evolved neural networks? So that's our research challenge. And of course, if we can come up with something that's interesting and that has literally hundreds of different behaviors and thousands of different pattern recognizer circuits and so forth, then that's persuasive. So I'm convinced of that. So hopefully a year from now at AGI-09, well, I have to. If I don't, so I hope I can present you something that's interesting and robots doing different things. And so now this is all very new, so it's I don't have an architecture yet. Okay, so the approach is fast, it's cheap, it's effective. I mean, in the sense they evolve. Where did this figure come from? How am I going for time?
You've got 2 or 3 more minutes.
Okay. So where did this figure come from? Well, if you download each evolved module from the board into the PC, and you do that tens of thousands of times, so it's tedious in that sense, then what's the maximum number of modules that your PC can signal, do the neural signaling, in real time? And what do I mean by real time? I define that to be every little neuron is signaling at 25 hertz. Right? Seemed to me a reasonable sort of number. And so we tested that empirically, and we found, depending on the PC, it was in this range, between 10,000, 50,000 little nets, each neurally signaled sequentially, right? Because the PC is monoprocessor. So the big question now is, what can you do with this number of modules? And my intuition says, well, probably a lot, right? Many hundreds of different behaviors and so on. Okay, what approach will we take? Eclectic. I'm reading neuroscience like crazy for ideas. Frankly, not very helpful. What is the thought? How do you make a decision? What's memory? Basic questions. Neuroscience still has to contribute a lot more than it has. Okay, so I'll take an incremental approach. I'll start very simply with like 20 modules connected, and then work up like 20, 50, 100, like the denominations of banknotes.
Hugo, you're initially going to work with a simple robotic system. Is that correct?
Yeah, I've got a.
So that since you only have a couple minutes, it might be worth connecting it to the robot interface for the audience.
Right, okay. So the brain itself you will not see. That will be in the PC. There's just large numbers of interconnected neural net modules. So what you will see is the behaviors of a robot. So the artificial brain in the PC will send out via radio antenna control signals to a robot. I have money to build a more interesting robot than the one I have. The one I have is just a little thing like this, about $1,000. So we will build a more ambitious robot with you know, eye vision, with hearing, arms manipulating.
It's a
maybe even a toy kitten.
It's a mobile robot?
Yeah, we'll make it, yeah.
It's
give it enough scope to be
wheels or legs?
Well, hopefully legs. Makes it more interesting. Okay. Okay, now I will not be talking about architectures because I just haven't done the work yet. It's still just the method. So next year. With Moore's law, pretty soon we're getting up to the possibilities like 100,000 modules, even 1 million. So problems. It's just not practical to evolve one module after another with these large numbers. So that's going to put pressure on a research topic of simultaneous multi-module evolution. How to do that? So that's a virgin field, just being waiting to be done. Okay, jumping ahead a little bit, just for fun. I'm anticipating that there will be national brain building organizations in the not too distant future. I mean, look at the history of the development of the rocket. Like in the 20s, Goddard, you know, this crazy guy, his MIT colleagues called him the Moon Man. It was a derogatory term because he genuinely believed with liquid fuel rockets, the principle would allow him to send rockets to the moon. But by the 40s, you had the V2, and when the German rocket scientists were captured by the Americans and the Russians, the Americans were surprised to learn that the Germans were surprised by the Americans' surprise because they said, "Oh, we learned it all from Goddard."
Okay. You guys got to wrap up now.
Okay, so Saturn V in the 60s, and so we have NASA, ESA, European, and so forth. So I see an analogy between all this and brain building projects. So China brain, A brain, America, J brain, and so forth. I'm contracted to write a book, if you're interested, but you'll have to wait 2 years. World Scientific, Singapore. So here's the title of the book on artificial brains. Okay.